Hello, everyone. Welcome to the Spectral Geometry and the Cloud seminar. Today, we have the pleasure of having Laura Monk from University of Bristol, who will speak about the moduli space of twisted Laplacians and random matrix theory. The virtual floor is yours, Laura.
Thank you very much, and thank you for the invitation. I'm very happy to be giving a talk here on this topic. So this is a very new research direction for me, so please bear with me for the historical imperfections, and I'm very happy to hear of any comments that any of you have, because this is really a new topic for me. So today I'm going to talk to you about a recent preprint I wrote with Jens Marklof on the moduli space of twisted Laplacians and random matrix theory. So I'm going to try and talk to you a little bit about random matrix theory first to motivate the results that I'm presenting. And so, yeah, here we go. Initially, one thing that happened is that people were naturally trying to understand the energy levels of big complicated nuclei, except the problem is that in order to do so, you need to diagonalize some Hamiltonians, and when there's a lot of different particles interacting, this becomes a very difficult mathematical problem. And a priori, in order to describe precisely the spectrum of one nucleus, you would have to, or one interaction, you would have to do things which are completely impossible mathematically and even experimentally, I think, challenging. And so in the 50s, Wigner had a very significant breakthrough in suggesting that rather we try and look at one specific atom and describe all of its energy levels, we decide to have a more statistical viewpoint and kind of drop the precise description of that specific system and think of it more as a black box and think, okay, I'm trying to diagonalize a very complicated matrix. So I won't know precisely what the eigenvalues are because I can't possibly compute them, or even I can't possibly do an experiment to access enough of them to understand the big picture here, because it's just too complicated. So rather than studying my specific system, I'm going to consider that it's a complicated matrix, a random one, and I'm going to hope that probably the spectrum of my system kind of looks like the spectrum of this very complicated matrix. So here you lose in precision because you will never be able to tell precisely the eigenvalues of your system, but maybe you might have some information about the density of the spacings or things, statistical quantities like that, rather than having specific information on your system, but more like the general picture. So in order to do that, what you would do is you would consider a big matrix and you will randomize the entries. So define a probability measure there. And you kind of want your matrix to be a reasonable description of your system. So you want it to be self-adjoint so that you can diagonalize it, but also because the Hamiltonian you're studying initially is self-adjoint operator. You want it to be representing kind of a physicsy thing. So you want it to be the distribution to be invariant when you change the basis. And you also want that if there's some symmetries in your system, which would be reflected in some symmetries in your Hamiltonian matrix, that they also are there in your new matrix description. So these are all quite natural assumptions you might want to make on your statistical model to model your Hamiltonian. Now, if you put all these conditions and on top of that, you assume some sort of independence of the different entries of the matrix, Dyson proved that there are three uniquely defined random matrix ensembles, which are called the Gaussian Orthogonal Ensemble, Gaussian Unitary Ensemble, and Gaussian Symplectic Ensemble. And that these are uniquely defined by this hypothesis, plus some symmetry constraints you put on your system, plus you assume that the entries are a bit independent from one another. So I won't define precisely those ensembles, but it's kind of the definition you would expect. You want to take a random orthogonal matrix with every entry of the matrix independent Gaussians. And obviously, you can't take all of them independent because you need your matrix to be orthogonal. So you also put the coefficients so that they're so that you get an orthogonal matrix. And same Gaussian Unitary Ensemble. Here you take a random unitary matrix with Gaussian entries. And symplectic, you take a random symplectic matrix with Gaussian entry. And so these three models are going to be the models you expect to see if you are trying to study a very complicated system which has time reversal invariance. So that means that if you look at your system evolving in time, and then you look at it with the time on reverse, it still makes sense, and your system still can reasonably evolve this way. The second one, if there's no such time reversal invariance, and the third one, if you have time reversal invariance, and also you have some sort of spin, which is related to some rotation in the symmetry of your system. So yeah, so these are the three ensembles which appear in random matrix theory to describe systems. Now, this was a very good insight, and actually, I think it's fair to say that it had a success far beyond the expectations that one could have of this hypothesis. So people started doing experiments and looking at the experimental data, and it complied to very, very, very precise level to these to these predictions. So here, the chart I'm showing you is a representation of a certain quantity which measures some statistical properties of your system. But the thing I want you to see is that this is compiling all the good quality data up to 82. So they did a survey of all the literature, every good quality data. The red dots are the experiments that they compiled. And the blue line is the GOE prediction with the error bar around. So this is very striking compliance between these experiments and the GOE prediction. So all these systems were with time reversal invariance, so it's normal that they follow the GOE line. So this was very, very exciting, as you would imagine. Now we have just some random matrices, and you can compute their spectrum, and it's describing some very complicated physical system. And it was so exciting that people started to think, maybe I can do that to other systems. Maybe I can do this to bigger things, more like large-scale questions. And actually, it was working quite well. And then Bohikes, Giannoni, and Schmidt in the beginning of the 80s had very big breakthrough when they realized that maybe, quite maybe, the reason why this statistics appeared, the reason why these random matrices were describing the system, wasn't really related to having a complex nucleus and with many different interacting particles, which was the hypothesis so far. So far, we thought it's because there's many particles, so I have a very big number of degrees of freedom. But actually, maybe it's related to having to studying a system which has some chaos in it. So to studying a quantum system which has a chaotic classical limit, so that it's not related to the complexity, meaning the number of independent moving parts in my system, but rather chaos. So you can think that's a bit of a connection between those two notions, because if you have a very complex system with many moving pieces, it's going to possibly behave quite erratically or chaotically. But in order to prove their point in this initial article, what they did is they studied a Sinai billiard. So it's a billiard, which is a square of which you remove a little disc in the middle, and you have your little billiard ball, and you hit it, and it bounces on the edges and also on the middle disc that you removed. And this is a very simple example of a chaotic system for which you can compute the spectrum of the Laplacian. So here, the quantum system is the eigenvalues of the Laplacian, and the chaotic classical limit is the geodesic flow. And the thing which is remarkable here is that they found the same chart as the one just before, meaning that the eigenvalues of the Sinai billiard were lying precisely on the GOE prediction, which is interesting because here it's not a big atom with a lot of electrons playing in all directions or protons or anything like that. It's one billiard ball living in a space of 2 dimensions. However, the system is chaotic. So yeah, their claim was that any system which is chaotic will have these random matrix theory statistics. And this has been a very influential claim all since the 80s. And it's been observed time and time again, numerically and experimentally, on many, many different systems. The exciting thing here is that if this random matrix theory comes from chaos, then it can be quite widespread. It can apply to many very different systems. So some special mentions here, for instance, would be that you can prove random matrix theories when you study zeros of the Riemann zeta function. And that here the kind of intuition is that the distribution of the prime numbers is chaotic, and that this would be why these random matrix models appear. So this is a statement about universality of statistics in the spectrum of a system, provided there's some sort of chaotic behavior in it. So I didn't manage to compile a nice list of references, so I'm lazily referring you to this beautiful Scholarpedia page, which I have been finding very instructive if you want to see really how far this goes and how it applies to many different things. So because it was such an exciting conjecture and really causing, I think, hundreds of thousands of articles or different settings to look at, there's been attempts to prove it, obviously, as you would. And there is a very nice, there's a lot of very compelling heuristical proofs of this conjecture, which I think are actually really nice to read, but they always have some kind of setbacks or some places where they're a bit wonky. So notably the kind of the good proof that you can have, one of the initial big heuristical argument was obtained by Berry using what we call the Gutzwiller trace formula. So it's a trace formula which you can prove for quantum systems. Now, if you wanted to do a rigorous proof, it's a bit difficult to think of doing a rigorous proof for any quantum system. This is a little bit too optimistic. So a very reasonable kind of way to tune yourself down and go looking a bit at a toy model is to instead of looking at every quantum system, I'm going to look at some which are very kind of easy to study, which are hyperbolic surfaces. So this is a very nice place for where we can try and test the conjecture and maybe hope to have a full proof. So to introduce things a little bit, so this the object I'm going to try to talk about are hyperbolic surfaces. I'm going to call them S today. By that I mean that they have a metric of constant curvature -1. So here I'm looking at surfaces which don't have any cusps or boundaries. So they just look like donuts with multiple holes. So here 2 holes, the genus. And so the Laplacian, so the quantum system I'm going to study here is to study the eigenvalue problem, so the eigenvalues of the Laplacian, which are a sequence starting at 0 and then increasing values. And so this is my quantum system. And the reason it's relevant to the conjecture is that the classical limit of this system is the geodesic flow, which is chaotic here. So we expect these surfaces to be very nice, simple examples of a quantum system with a chaotic classical limit. So it's quite common in it's very common in hyperbolic when you study hyperbolic surfaces to do a change of variable and write lambda j as 1/4 plus rj squared and study the rj's instead. So now, how would you possibly test this conjecture? You gotta pick something to observe and try to compare it to your random matrix prediction. So there's many things you can possibly try and observe. And the idea will be, I compute something and I compare it to a random matrix prediction. Maybe I find the same thing or maybe I don't. So an example of something to check, to have a look at would be the variance of a counting function. So I'm going to introduce this here. So I'm going to take an even test function f with compactly supported Fourier transform, but mostly let's think about this f as a little bump, like this little bump here. And I'm going to pick two parameters, tau and L, which are where I put my window and how wide my window is. And then I'm going to use my little bump, my little f, and I'm going to like rescale it and replace it to be looking at some place. So here I want to look around the value tau, and I want to look at a scale 1/L. And so I construct my function HL tau by moving and dilating f to be looking around this value at this scale.
Excuse me, Laura, is it f or the transform of f that is the bump function?
So it's kind of f. Unfortunately, you have to assume f hat of compact support, so you won't be able to take f to be completely compactly supported, therefore.
Okay.
So yeah, it's going to decay, but not as nicely as the picture kind of leads you to think. Yes, very good question. And so then you can use my little test function here and sample it over all the RJs. So the RJs, remember, they're the spectrum, basically. And it's going to more or less count how many RJs live here. And we get this little smooth counting function. So it's smooth because I use f and not an indicator function. And it's counting basically how many eigenvalues there are around this value tau. So now, one thing you can do, but there's many things you could do. You could do much more detailed things, but one like little first test you can do is to compare, say, the variance, so what variance with regards to what we'll see, but the variance of this counting function with the prediction from random matrix theory. So random matrix theory tells you that if you computing this now for your random matrices, not for your hyperbolic surfaces, but for your random matrices, you expect the variance to look like this integral. And there's a constant in front of this integral, which depends on which model you have in random matrix theory. So the constant is going to be 2 if you're looking at the Gaussian Orthogonal Ensemble, 1 if you're looking at the Gaussian Unitary Ensemble, and 1/2 if you're looking at the Gaussian Symplectic Ensemble. So this is really nice because you have this form of the expected variance that you should get as an integral of x times the Fourier transform of f squared. And also the different models lead to a different constant in front of this integral. So actually you can differentiate between the different models. So now the aim is of the rest of my talk is going to be to try and do this with random hyperbolic surfaces. So the variance here is going to be by taking a random surface. But first, before we actually do this, I want to tell you a little bit more about the heuristical proof for hyperbolic surfaces. And I'm going to talk to you about this proof in the case where there's time reversal invariance. So we study exactly this problem, exactly this question, but for a fixed surface, and we wonder, does my spectrum look like the Gaussian Orthogonal Ensemble? So there's numerical evidence. In this article, they sampled some surfaces of genus 2, and there's a nice compliance with the prediction. But here I want to tell you a little bit like how you would go about it, because this seems like quite a difficult mission. So how would you go about it a priori? So the way you would go about it clearly, like this is clearly the way for hyperbolic surfaces, is to use the Selberg trace formula, which is the friend in the world of hyperbolic surfaces to the Gutzwiller trace formula I mentioned just before. And what it tells you is that this variance of my counting function, so the thing I want to study, my variance here, you can rewrite as the variance of now an oscillating counting function. That's why I call it OSC here. And my oscillating counting function, now it's no longer a sum on the spectrum, like initially my friend, the counting function here, but it's now a sum over all the geodesics on my surface, closed geodesics on my surface. So here I have my little surface, and the loops or the curves, the closed curves I draw here, they are closed geodesics on my surface. They're primitive because I only go through them once. Yeah, they would be not primitive if I decided to go twice along the same curve. And there is a countable number of them, so I can sum over this family of closed geodesics. I can sum over the iterates, so that's why I take primitive ones, because I'm going to then go through the geodesic multiple times. And then I sum this function, which is explicit and depends on the length of gamma. So this is the length of my geodesic. And importantly, what I'm going to do is I'm going to have the Fourier transform of my test function. So in my initial quantity here, in my initial counting function, I have h. But now in the oscillating version, what's going to appear is the Fourier transform of h. And that's why I call it an oscillating test function, because the Fourier transform of h, there's going to be some oscillations in it compared to h initially. So yeah, so you can use the Selberg trace formula to tell you that computing the variance of my counting function is the same as computing this variance of this geometric function, which is oscillating. So this seems nasty. This doesn't necessarily seem much simpler, but there is a very beautiful insight that you can have here, and that is Berry's diagonal approximation, which is that when you compute the variance, you're computing the square. So you take the square of this oscillating function, because the variance, there's a square in it. And so you have a square of a sum. So when you take the square of a sum, there's a sum over the pairs which appear. You have the square of the sum of a gamma, it's the sum of a gamma 1 and gamma 2. And when you work it out, you will have some terms which compare the Fourier transform of your test function at L gamma 1, of the length of gamma 1, and the length of gamma 2. So in this Fourier transform, you can check, do a little computation, and you're going to have a phase which is oscillating at the speed, which is the difference between the length of your two geodesics. And the idea of the diagonal approximation is that basically if gamma 1 and gamma 2 are not the same, well, the length of gamma 1 and gamma 2 are not going to be the same, and this is going to oscillate, and therefore it's going to be small. Compared to if gamma 1 and gamma 2 were the same length, this phase would be 0 and it's going to stay put. So if gamma 1 and gamma 2 are the same or reverse to one another, they will have the same length always, and this term is going to not oscillate. But otherwise, I'm going to consider that it's oscillating and throw it in the bin. So this is a big jump. This is a typical physical jump that you have to do in physics, which is like, well, I have an exponential which is oscillating and the phase is not 0. I'm going to consider that this term doesn't count. And a priori justifying this can be very difficult. But it's a logical heuristic that one would form. So, okay, so just to wrap this up, so the diagonal approximation tells you that I'm going to consider that if we don't have the same geodesic or the geodesics and its opposite, this is going to oscillate and it's not going to count. So I throw away every term except the diagonal terms, which are gamma 1 equal gamma 2 or gamma 1 equal gamma 2 inverse, which are terms for which the length will always be the same.
Also, yeah. Laura, there could be different geodesics that have the same length, no?
Definitely, and there is actually. We know that there's repetition in the length spectrum. So this is a bit questionable. This approximation, you would have to work a lot to make that a real thing a priori.
Thank you.
So it's very like not gonna work like this in real life, but it's an interesting heuristic. But there's a priori there's other pairs of geodesics which always have the same length, so you can't do that. Yeah, definitely. So that's the first step of the proof. That is the big one, which is a bit wobbly, I guess, and which we would need to work a lot to justify. And then the second one, which is a little bit less of a jump, but still there's a bit, it's not easy to justify it fully for a fixed surface, is that we have the prime geodesic theorem, which tells you that the number of primitive closed geodesics smaller than a certain length L behaves like exponential of L over L. And so now you can take your variance, you just keep in the sum of the pairs gamma 1 and gamma 2. And you say that you have a sum, you compare it to an integral, and you have this density appearing, which is then because there's this number of terms in your sum. And you work it out just simply like I'm computing a sum, I compare it to an integral, so I need to put in the density, which is given by this thing. And then you get actually the prediction of the Gaussian Orthogonal Ensemble. So these are two big steps in the computation, which a priori you can't make them fully a proof for just taking a fixed surface. But it's quite an exciting and compelling argument. So now my question is, can you actually make it work? Can you actually prove something rigorous entirely, and not just like kind of a formal computation with some skips? And in order to do that, one natural idea is to study random hyperbolic surfaces, which give you a lot more power tools. So in order to do so, what we're going to do is we're going to fix a genus G, which is greater than 2. So the genus is the number of holes in your surface. It was 2 in my pictures. And we're going to consider the set of all possible hyperbolic surfaces of genus G, which are called the moduli space. So it's just all these surfaces of genus G, or the hyperbolic surfaces of genus G up to isometry. So it's really all my possible surfaces. And actually probably can't, okay, and this set comes equipped with the Weil-Petersson probability measure, which I denote like this, which is a very pretty measure. Basically, it's the Lebesgue measure on my set, and it's very nice, lovely, and it's a very natural model that you might want to study on your set of surfaces. And last year, Rudnick proved exactly what I've been hinting at, which is that if you take a large genus limit, so there's a bit of a specific scaling regime here, so you have to take large genus limits, but in that limit, the variance of my smooth counting function among surfaces of genus G is going to be the GOE prediction plus something that becomes small when L goes to infinity. So if now G and L both go to infinity, we have this GOE limit appearing. So that's very exciting. And the proof of this result is the same proof as Berry's proof that I just outlined before, basically. But you make it rigorous using results of Mirzahani and Mirzahani-Petri. So here there's kind of really these two steps. And what's beautiful with this model, with this Weil-Petersson model, is that both of these steps, they become explicit integrals that you can actually compute and do like integration by parts, or just this density argument here is just like actually we have an integral version of it, which is completely just closed and precise formula. Because we take random surfaces, these two steps, they just become completely clear and precise because of this additional tool of having taken an actual average over the set of all surfaces. So there's also further works with this, developing the same ideas in these articles of Rudnick with Wigman. And in the meantime, since Naud had found same results for random covers, where it's a bit more difficult because it's another model for random surfaces. It's not the Weil-Petersson probability measure, but another model, which is discrete. So you have a bit less averaging tools, and it's a little bit more difficult to make the argument work. But in this model, there's GOE and GUE statistics depending on whether or not you have time reversal invariance. But this is another model which is discrete and doesn't describe all of the surfaces. And in this article, Naud asks the question, can you redo the same thing as Rudnick did, but in a now having broken time reversal invariance, and can you find other statistics, so the GUE, for instance? And this is what we did in the article with Jens this year. So we defined an extended notion of the moduli space, so of my space of surfaces. And we defined some new probability measures. And thanks to these new notions, we defined some new I'll tell you everything in more detail just after that, but we obtained for these kind of random surfaces a counterpart to Rudnick's result, but now with GUE and GSE statistics. Okay, so yeah, so I'm going to walk you through the construction a little bit before I can claim the result. So, but basically what we did was define a new probability model which describes all the hyperbolic surfaces, but in which we break time reversal invariance and in which we put in a spin to be able to find not only GOE here, but the other random matrix models that you expect, so GUE and GSE. Okay, so the heuristic is actually can be found in literature once again in physics, and it is to add a magnetic field. So for my hyperbolic surfaces, I have these geodesic flow, which is my chaotic classical limits. And the heuristic here is that if you take a geodesic and then the inverse of your geodesic, it's the same. So there is this time reversal invariance. If I see a particle moving on my geodesic, and then I switch the time the other way around, I see the same thing, and both are legit trajectories. But if you add a magnetic field, because the particle is twisted by this magnetic field, it's not going to be the case. You can't reverse the time and find the same trajectory anymore. So this is the heuristic, and this is the thing we did. So before, we were studying the eigenvalues of the Laplacian, and now we study the eigenvalues of the twisted Laplacian. So we add a twisting. So before, we were studying a surface S, which you can obtain by taking the hyperbolic plane and taking a quotient by a Fuchsian group, gamma, which is going to be the fundamental group here of my surface. And now, on top of that, I need to add a unitary character, which is going to be basically my magnetic field. It's going to tell you how the impact of my magnetic field on my surface. And once you add this data, you can define the twisted Laplacian. So I'll just give you a little definition. So when you define the Laplacian on your surface initially, what you do is that you take the Laplacian on the hyperbolic plane, which has this nice form. So it's y squared times the sum of the derivative of order 2 in x and y. That's the definition of the Laplacian on the hyperbolic plane. And then in order to define your Laplacian on your surface, what you do is that because your surface is a quotient, you can just restrict this Laplacian to functions which are invariant by your group. So you want to just consider functions on the hyperbolic plane, but which are invariant by your group action. So that they induce a function on your surface. Now, if you add a character, you just do exactly the same thing, except now this transformation here, the action of gamma on the point, is going to be twisted by this character. So rather than looking to functions which you can take the quotient by your group and obtain something well defined on your surface, there's this number here on the unique disk, which appears. And this is the way you define your twisted Laplacian. You take the restriction of the Laplacian on this set of functions. You also have an eigenvalue problem, once again, and you can study the eigenvalues of this twisted Laplacian. And you also have a Weil-Petersson formula, once again. So you can also bring yourself back to studying this function that pops up in the Weil-Petersson formula. The only difference being that now you have this oscillating term here, an additional oscillating term, which comes from a character. So this is, you got to think about the fact that, so when I say it's a unitary character, so its values are in the unit disk. It's complex numbers of modulus 1. So this is going to be powers of a complex number of modulus 1. And that's the only thing that is going to change the heuristics, is that this extra little factor here is going to appear. But now, when you do your proof by diagonal approximation, you remember there was the terms gamma 1 equal gamma 2 and gamma 1 equal gamma 2 minus 1, because the length of gamma 1 and gamma 1 minus 1s were always the same, so both those terms would appear, and they would lead to the GOE prediction. However, now, if you take the term gamma 1 equal gamma 2, what appears is the modulus square of the character, which is 1. So this term is still going to appear. But now, because we broke time reversal invariance, actually, the other term, gamma 1 equal gamma 2 minus 1, even though the length will still be the same, so the phase appearing from the Fourier transform will still be 0, you will have chi of gamma 1 square appearing here, which a priori has no reason to be 1.
Laura, I have a question again.
Yeah.
Yeah. How do you see that some time reversal is broken? Is that some classical counterpart to what you're presenting, where you would see this?
So this is so I haven't exactly said it yet. So here, actually, what this kind of thing tells you is that you break time reversal invariance when you break the symmetry between gamma and gamma minus 1, between the geodesic and its reverse. And if you look at your system, this means that you take a character which is not real valued, because if you have chi of gamma minus 1 will be its complex conjugate. And so it is in this relationship, in the fact of having a non-real character, that is going to be the time reversal invariance breaking. So if you take a character such that gamma is real valued, this power here that appears is going to be the same for gamma and its inverse. So you will not have broken the time reversal invariance. But if you take a character which is not real valued, gamma and gamma 1 are going to have different values in this oscillating function, and you will have broken time reversal invariance. If that makes sense.
Is there like a ODE similar to the geodesic equation where something will also change in the more classical counterpart for the...
I actually wondered when I was starting to talk about this. So if anyone knows, welcome to share. I don't know.
Okay, thank you.
Yeah. But so the heuristic here now is that you still have your term gamma 1 equal gamma 2, which is the diagonal up term, which will still give you something. But the second term here is not going to give you this term anymore. And if you manage to say that it's small, if you manage to justify that this is oscillating and therefore not really there, you only have half of the terms that you have before, which gives you the GUE, because actually the prediction of the GUE is half the prediction of the GOE. So really, the thing I want you to take away from this heuristic is that before we had two contributions, gamma 1 equal gamma 2, or gamma 1 equal inverse of gamma 2. And that's because gamma 1 and its inverse, they had the same length and they were the same in your system. And now only one of those two contributions will yield the expected contribution, and the other one will be small. And that's because we broke the symmetry between gamma 1 and its inverse, which corresponds to taking a non-real character. Okay, and so that's what we actually did with Jens. So in order to do that, we need to define no longer a probability on the set of surfaces, but on the set of surfaces plus my character. So I need to define an extended moduli space, which is the space of all surfaces plus my character here. So it's going to be basically a set of all the possible twisted Laplacians. So let's try to have a little think about what this space looks like. In order to do so, if I fix a surface S, so that's my surface friend, I put a surface of genus 3, I can define a family of loops, of fundamental loops on my surface, AI and BIs. So there are a family of fundamental loops. What that tells me is that they generate the fundamental group. So any loop on my surface, any gamma, I'll be able to write as a combination of those loops. And so if I have a gamma in pi 1 of S, so an element of my fundamental group, I can write it as a combination of these. So for instance, here gamma, it's kind of following B1 minus 1, and then and then B2 and B3. So here we have gamma is minus B1 plus B2 plus B3. And I can associate a vector in this basis, which tells you how many times gamma goes along B1, B2, B3, A1, A2, A3. So here, gamma 1 is going to be 0, 0, 0 for all the A1s, minus 1 for B1, 1, and 1 for B2 and B3. So it's a vector of integers, which is the homology vector, and telling you just how many times gamma winds along every of your geodesic, of your little fundamental loops. And the data of my unitary character, so of my chi here, is equivalent to the data of a vector on the torus, so a vector theta on the torus of dimension 2g. So here the torus is just r to g quotiented by z to g. And the correspondence between those two is that if I have a theta, I can define a unitary character by taking this exponential. So exponential of 2i pi theta and the homology class of gamma. So here, theta is telling me basically how much the impact of the magnetic field on when I wind along theta 1. So every time I'm going to wind along one of these fundamental loops, I'm going to win to get hit by the magnetic field quantity exponential 2i pi theta I, where theta I is the corresponding component of theta. So what that tells me is that this moduli space here, which is the set of all possible S's and all possible chi's, is non-trivial fiber bundle. I hate doing this to you because I hate it when when the fiber bundles and all that appear. Sorry. So it tells you that basically for every point in MG, for every S, the set of points in MG tilde, which has this S, so the set of all possible chi's, is basically a torus. So it's a torus, sorry, I didn't say, but it's a torus because if you add an integer to theta here, because of the periodicity of the exponential, it gives you the same character. So these two characters are the same. So that's why we consider them to be up to integers. So a point of the torus and not a real vector. So basically we have my moduli space, but I added an extra data on every point, which is a vector theta, which tells me what my magnetic field is. Now I want to define an invariant probability measure.
Excuse me, Laura, I have a stupid question about this. Is it the product or is it a non-trivial bundle?
It's non-trivial because here there's an action which is hidden, which is the action by the mapping class group, which just basically is all the symmetries of your surface. and this corresponds to an action of the symplectic group on the homology, which we know is non-trivial. So sorry, a bit of a technical answer there, but it is non-trivial.
Okay, thank you.
Okay, so now we want to define what a random pair S and chi is, so a random twisted Laplacian. And we already know what a random surface is because we had this beautiful Weil-Petersson model. So the only thing we need to do is make sense of what a random chi is, and then make it so that the definition works all together on this new space that we introduced. And there's quite a lot of natural probability measures that one could consider. We need them to be to have some properties in order to define a probability measure on the whole space. And so for that reason, what we picked is to take some probability measures, which is to take a family of probability measures, nu q. So one of them is q equal infinity is Lebesgue measure. So we take any theta on the torus. And the other ones are discrete measures, which are supported on the rational, the fractions of a denominator q. So in order to see that, what's gonna now so this density here is gonna charge a certain lattice on the torus. I find the nicest way to view it is that if we look at the thetas for which this is not zero, and we look at exponential 2i pi theta, which is the magnetic field that's gonna appear, when q equal infinity, any value on the unit disk will appear. So I'm really taking a random value on the unit disk uniformly. But then for other values of q's, I'm going to take just the unit, the square, like the roots of unity of degree q. So for instance, for q equal 8, I have these 8 values which can be taken with uniform probability. For q equal 3, I have these 3 values. And interesting thing is that for q equal 2, I'm going to take only +1 or -1 with equal probability. And for q equal 1, I will have done nothing because my magnetic field is always 1. And now we can just define the probability measure indexed by q on my extended moduli space by sampling my surface according to the Weil-Petersson probability measure and my angle according to these non-discrete or discrete measures on the angle component. So this is a very natural way to define some measures on my extended space, which is a fiber bundle. So interestingly, as I was telling you, the cases q equal 1 and 2 are a bit different because when q equal 1, chi is always 1. And when q equal 2, chi is always +1 or -1, so it's real valued. So we always have that the conjugate of chi is itself. So that means that in both those cases, we have not actually broken time reversal invariance, and it's preserved. However, for q greater than 3, we can compute just by looking at these at the values here, which are taken by my distribution, that the probability for chi bar to be equal to chi is going to be, it's very explicit, very straightforward computation, just by looking at the values taken by my distribution. And it's going to be a number, when q is greater than 3, a number smaller than 1 to the power g. And when q is infinity, it's going to be 0. And in all those cases, it's going to go to 0 when g goes to infinity, which is the regime that the Rudnick result was in. So in the asymptotic regime where we take g going to infinity, we take very big surfaces, time reversal invariance is broken with a high probability, with a probability close to 1. And therefore, and actually, we have extended Rudnick's result, and we can prove that the limit when g goes to infinity of this new variance, so here now there's a new parameter q, which tells you which distribution you pick for your magnetic field, but we have this variance, and we find that it goes to the GOE if Q equal 1 or 2, so when we did not break time reversal invariance. And it goes to the GUE if Q is greater than 3 when we did break time reversal invariance. So that extends Rudnick's result to this new probabilistic model where we have added the magnetic field. And thanks to the addition of this magnetic field, when it actually causes the time reversal invariance to be broken, we do see GUE statistics appearing. The key ingredient in the proof, in my opinion, is that we can integrate on every fiber. So that's what I'm going to try and explain here. So if we consider a measurable function on my extended moduli space, so my space of my surfaces plus my magnetic field, we can take the fiber average, which I note here with a little hat, I don't know how to call this guy, a weird hat, so I have a function which depends on my surface and my chi, but now I want to make it into a function just for my surface, and to do so I integrate over all possible chi's on where my surface is, so on the fiber. So the average applied to a surface S is going to be the integral of all possible f of S and chi, where chi now is taken over all possible chi's, so it's integrated over a torus. So I'm just taking a random magnetic field, and I average over all those random magnetic fields. And it's straightforward, thanks to the fiber bundle situation here, that taking the expectation of a function for my new model, or the probability measure that we defined, is the same as taking the average just in terms of surface of the average. So in order to take the average over all possible surfaces and magnetic fields, it's the same as to take the average first over all possible magnetic fields by fixing a surface, and then taking a random surface. So this is just a way to cut the integration by saying I can average over all my space, or I can average over each fiber, and then the base space. And what we do is we use this to reduce the computation of the variance to some computations similar to Rudnick's paper. Because here I have an expectation for my new probability space, but this brings me back down to taking some expectation for the Weil-Petersson space, which we have tools for. So this allows you to go from a problem where there's a magnetic field to deal with to I average over all magnetic fields, and now I just have a function of my surface. In particular, if you remember, in the heuristics, there is this term, gamma 1 equal gamma 2 minus 1, which is the sum of all the possible gammas. There was this quantity which appears in the square, and we had this chi-square. And what we show is that this expectation, it's going to be 0 if Q is greater than 3, and as long as the homology class of gamma is not 0, but because if it is 0, this is always 1. And this is the key little step that allows us to reduce ourselves to the computations in the Rudnick paper. So now there's an open question, which is here we had to average over all possible magnetic fields. Do you have to do that? Can you study some twisted Laplacians without averaging over all possible fields? So that would be actually quite interesting questions to look at. I'll just say a little final word about the GSE statistics, which is that our model also allows to construct without any further definitions of moduli spaces and everything, random Dirac operators. And when by constructing this, we find the same result, which is that now for the Dirac operator, we have, so this is an old version. There's a big O here, which I forgot to put. So there's a big O in both lines. It's the same big O. But the key thing here is that you get GSE statistics when Q is 2, in which case you have a spin and time reversal invariance, and GUE statistics otherwise. So I won't have time to talk to you about all of this, but basically the setting is that the Dirac operator is an operator acting on functions now which go from H to C2 by this matrix, which is a degree 1 differential operator. And before, in order to define a twisted Laplacian, we had to define a chi. Here it's also the case, except the Dirac operator on the surface is not going to be given by a unitary character on pi1, but on pi1 of S bar, which is a double cover of pi1. So sorry, I don't have time to talk about all the details here. With the extra condition that chi of -1 is -1. And so that corresponds to also giving yourself a vector. So actually, you don't need to construct a new moduli space or anything. The one we defined, the mg tilde, is enough to here also construct a random Dirac operator, because the only thing you need to give yourself is once again a theta. Except now it's not very natural because we have this condition that the character applied to -1 has to be -1. It's not very natural to take any value of q. We have to take q even so that the distribution on the circle is symmetric or infinite. And because of the symmetries of the system has different symmetries depending on whether or not there's time reversal invariance, and that's what gives you those different results here. Yeah, sorry for the slight, like the Dirac case, I haven't exactly laid in every detail, but I did think it would be a little bit too much. We've already talked a bit about a lot of things during this talk, so I thought it would be a little bit too much to go in detail. So just giving you a tiny little glimpse in this case. But basically, all the things that are set up for twisted Laplacian, they work the same for Dirac, and then it just becomes a question of like adapting the argument, which is very straightforward because that's once again a cell-Beck-Trace formula, so everything works pretty much the same. Thank you very much for your attention, and I'm happy to have any additional questions.
Thank you, Laura, for the talk. Do we have questions now? We have time for questions now.
Yes, I had plenty of questions, and thank you, Alexandra.
I think I spent the whole talk trying to make precise the question I have, and I'm not sure that it's yet very precise. But I guess in a way, there's always these universality classes with GOE, GOE, and GSC appearing in these cases. Is it because we always look in a way at Laplacians and Dirac operators, or even more general classes of operators would?
So here you don't have to have any operator for the result of Dyson I was telling you about at the beginning.
Yeah.
Which is that so here it's really like if you assume that you have some sort of independence in the entries of your matrix, which is not necessarily something you need to assume, but if you did want some sort of independence in your entries and you wanted the symmetries which correspond to the different symmetries to appear, this is the ensembles, they're uniquely defined by these properties. So now the question is, do you have systems which have even different kind of symmetries to look at? But
yeah, in a way, different sort of symmetries or different. Does it make sense to look at other type of spins? I mean, these are very naive questions.
So if you have integer spins, I think you go back down to one of those two. And
Okay.
I mean, yeah, so all the combinatorics of all the different cases are tailored. I just didn't put all of them here. So you always bump back down on one of those if you take something else. So for instance, if it's not half integer but integer, you have one of the first two. I don't remember which. And see, we got a glimpse of that here at the end, because for Dirac here, you had, in the case spin 1/2 and time reversal invariance, you did get GSE, but actually if we take Q different from 2, we break the reversal invariance and we go back on GUV. So
yeah, okay, I see.
But yeah, I agree. It was very surprising to me. I was always like, but why just these guys? So there's generalizations you can do to have more sets of more ensembles, and they are studied, and there's interesting things to say about them, but I don't know much about that.
Okay, I see. Are there other questions for Laura? I presume that the questions were addressed during the talk. And so let's thank Laura again for the very nice presentation. And we will reconvene next week at the same time with a talk by Amir Vig, who will tell us about Mach length spectral invariance of Birkhoff billiard tables and compactness of isospectral sets. So until next week, thank you very much and have a good time.